Hey kids, we are back. Hope your AP tests went well, and we are continuing on with derivatives. Some of you may know this rule already, but we are in fact learning the power rule for derivatives today, which you still need to know those limit rules. F of x plus h minus f of x over h as h approaches 0 will give you the derivative. Trust me, your teacher will still find a way to test you on that, as will the AP exam next year. But there is a fast way to get the derivative if you have an expression basically in polynomial format. So if you have this x to the nth, then the derivative f prime of x will always be this. If you didn't notice this pattern or no one told you about it, you didn't look it up, it will always be whatever this power is multiplied by the coefficient. So it will be, if that's a 1, it'll be n times 1. If it's a 2, it'll be n times 2. N times x to the, and the exponent decreases by 1 each and every time. I don't know if you ever knew that, but take a look back at some of your derivatives when you did them the long way with Pascal's triangle or whatever, and take a look at the final answer compared to the original equation. That's the pattern there. So it's very cool, helpful. It allows us to solve bigger problems faster and to get right to it. So let's just try a couple of these. So differentiate each expression. Differentiation is the process of finding a derivative. We're still building that vocabulary while we learn this new stuff. And notice the notation here. This is an expression, not an equation. It's not y equals or f of x equals. But this Leibniz notation, as it's called, can be used like an operation. You know, similar to if I said take the square root of all this, or the sine of all this, or the natural log of all this. I can say find the derivative of all of this with respect to x. And again, as long as this variable matches the variables you're dealing with, you're all good. And at this point, they should. So I don't expect you to have a perfect understanding of this notation just yet, but that's how it starts. You start to make an effort here. So the derivative of all this equals, so since it's an expression, I get an expression. There's no y prime equals or f prime equals. And you take the derivative of each term. So 5x cubed, we apply this power rule. 3 times 5 gives us 15, x to the, and you subtract 1 from the exponent. 3 becomes 2, it's 15x squared. Now you move along to this term. Derivative of negative 7x squared. 2 times negative 7, negative 14, x to the first. 2 minus 1 is 1. We don't need to write that. And the derivative of 5, the derivative of any constant is going to be 0. And you can think about that a couple ways. Hopefully it totally makes sense. One way to think about it is applying this very strict power rule that if it's a constant, that means it's really like 5x to the 0. And therefore, when you do 0 times 5, or 0 times whatever constant, you get 0. 0 times x to the negative 1, and that's just 0, so it drops out. You can also think about it like this, which is nice to understand and make this connection, that any constant, think of the graph of any constant, y equals 5 in this case. If you think about that graph by itself, any constant is just a horizontal line. Regardless of how high or low it is, it's just a horizontal line, and the derivative represents the slope of that. And so if you're talking about a constant, the slope will always be 0. There's 0 change in it. So that's why, again, just another proof of why the derivative of a constant is 0. So that term just drops out. Boom, there's your answer. Okay, so notice this is all in terms of w, and we're saying find the derivative of all of this with respect to w. That's what the denominator tells you, is with respect to what variable. And these are all w's, so we're good to go. So let's use our power rule here. 7 times 8, 56. W to the, subtract 1, you get 6. 4 times negative 5, negative 20. W, subtract 1 to the third. This is already a 1. 1 times negative 12 is negative 12. And it would be w to the 0, which means I get a constant, so I leave that. This is a constant, so the derivative of any constant is 0. Gone. Boom. And there's our answer. You are still welcome to use the limit rule if you like and do 8 times w plus h to the 7th and expand that and do all the canceling out, and it feels pretty cool to do it. But we're going to move on to bigger and better problems, so this is what the rule is all about. How nice, right? And it's, of course, a great rule. It's very easy to use. I doubt you'll forget it anytime soon. The problem is it's only works if you have something in this kind of polynomial format. So if it's not in that power rule format, that polynomial format there, then you have to say, can I get it into that format before I use the power rule? And if you can't, well, then you can't do the power rule. And the power rule doesn't work on everything. So we're going to talk about that, and often you're going to have to rewrite your function before doing the power rule to it. For example, this, y equals 2x to the 5th cubed, and we want to do the derivative of this. Well, first, I need to be in simplified polynomial power rule format. So I got to cube each of these things, right? This term. So 2 cubed is 8, x to the 5th cubed is x to the 15th. Now I haven't done anything other than simplify that, so that is still just y equals. But now it's in that power rule format. Now I'm ready to go. And so here, my derivative, and this is where you want to distinguish that this is now a new equation. Don't just keep writing equals, otherwise you're saying this equals the thing. No, the derivative of this, y prime, or dy dx equals. And power rule on that is 120 x to the 14th. There is our derivative, right? Okay, so be good about your notation, not just the rule. The rule is simple, takes 30 seconds to learn. But build that in and be good with your, showing distinct steps. Okay, this right here, definitely not ready to do the power rule on this. Look at this, you got to simplify this. So I've got 2x. I've got to square this binomial. That's going to be x to the 4th minus 6x squared plus 9. Foil that out if you have to. And I still got to distribute the 2x. It's not in that polynomial format. So 2x to the 5th minus 12x to the 3rd plus 18x. And you see now it's ready to go. It's in that polynomial power rule kind of format. So y is equal to that, and here I'll go out of my way to use the Leibniz notation that you can maybe see again, like how it's used. I could now use I could take the derivative of all of this with respect to x. And see, I can use it as an operation. See, on this side, you kind of take for granted the derivative of y with respect to x is dy dx. And now the derivative of each of these terms with respect to x will be 10x to the 4th. 3 times negative 12, negative 36, x squared. 1 times 18, 18, x to the 0, so just 18. And there is our rule. And of course that means the same thing as if you had written y prime equals, but just nice to see these, this notation getting mixed in and try and get as comfortable as possible. There you go. Hey, lots of radicals, lots of complex fractions, lots of things like that. So, the rule itself, that's the only calculus. It's actually a lot of algebra after that, just basic algebra, dealing with exponents. So be good with that stuff. I'm going to rewrite this again in that power rule format. So I need to see it as a coefficient times x raised to some power. So this is 6 times x, and since it's the cube root, that is really x to the 1/3 power, right? Power over root. That's 1 over 3, 1/3. And now I can treat it just like all my other polynomials, even though this is technically not a polynomial. The derivative of this, the original is h, so I should be calling it h prime. If you write y prime or f prime, you're not using it right. 1/3 times 6, 2, x to the 1/3 minus 1. Okay, you got to do a little subtraction here. 1/3 minus 1 is negative 2/3. Now, you might have some teachers who will let you leave that final answer there just as is. I tend to prefer you to never leave negative exponents in a final answer. So I'm going to say in my class then I'm going to rewrite this. Now the 2 doesn't have a negative, so you leave it where it is. This goes to the denominator and becomes x to the positive 2/3. Now that is really like a radical in the denominator. It's the cube root of x squared. But this, and I'm sure most teachers are kind of on board with this in the calculus level, you do not have to rationalize any functions because it's just a function. It's not a number. For all I know, I could be plugging 1 in there for x and there's no radical left. So if you have a function, you do not have to rationalize it. You could change it back to radical form if you want. That would be equally good. If you do rationalize it, that's fine as long as you do it right. But for me personally, I like no negative exponents in the final answer and no complex fractions. So we're good there. Every teacher, professor is going to have their little preferences, so it's up to you to just kind of adapt. G of x is 5 over 3x squared. Again, this is not in power rule format, but I can easily express it that way by thinking of this as 5/3 as the coefficient, bringing that x up, and that's really x to the negative second. So again, being good with your algebra of dealing with exponents. And now we're ready to go. So g prime of x is equal to negative 2 times 5/3 is negative 10/3 x to the subtract 1. And these are actually where a lot of the silly mistakes happen, is just subtracting from a negative. So negative 2 minus 1 is negative 3. I don't like that as a final answer. Move it back to the denominator, make it positive. So negative 10 over 3 x to the 3rd power. Done. Very nice, right? Okay, let's just try a few more just to see some more examples and to be comfortable. But like I said, you've learned the power rule now. It's just a matter of knowing when you can apply it and applying it properly. This right here, can I apply it as is? No. Let's express this in exponential form. That's 6x to the 4th times the square root of x cubed. Well, that's x to the 3/2, right? That square root is really a root 2, so denominator 2. And this, I cannot take the derivative of with the power rule. I need to put those together. So that is 6 times 1 is 6. X to the 4th times x to the 3/2. What do we do when we multiply? We add those exponents for those common bases. So 4 plus 3/2, that's 8/2 plus 3/2, that's 11/2. And you see, you can already start to imagine these are the places where I'm going to get silly mistakes. That is still just y. My derivative, dy dx, or y prime equals, now apply the power rule. 11/2 times 6 is 33. X to the 11/2 minus 1, so minus 2/2 is 9/2. No negative exponent, I'm fine. If you want to change it back to radical form, call that the square root of x to the 9th. Fine. If you want to simplify the radical and pull out, x to the 4th, whatever, go for it. But I'm fine with that. Number 8, we got, again, just a radical. It's in the denominator, so we're kind of putting all the ideas together here. That this is, just take your time. The cube root of x squared is really x to the 2/3. Just watch that power over root. And if it's in the denominator, that is really 7/5 x to the negative 2/3. Doing those two maneuvers is often mishandled. So now our derivative of that, it's in that power rule format. Y prime is equal to negative 2/3 times 7/5 is negative 14/15. Yes, you have to know how to add and multiply fractions. I know it's not fair in calculus. X to the subtract 1, negative 2/3 minus 1 is negative 2/3 minus 3/3 is negative 5/3. Gonna leave it? Nope. Gonna move it back to the denominator. Don't like negative exponents in my final answer. Negative 14 over 15 x to the positive 5/3. I'm going to stop there. You can change it to radical form, you can simplify, you can rationalize, you do whatever you want as long as you do it right. But there we go. And lastly, here's one problem here. Taking the derivative of a big fraction like this, hopefully you realize that you can't do the power rule to this, and you're going to learn something called the quotient rule eventually, which you can't just do the power rule to the top and the power rule to the bottom. That's just too simple, and it doesn't work. Usually things too good to be true are. But this is what I call a moo problem. It's kind of a stupid name, and it just helps you remember. Moo stands for many over 1. Many over 1. And that is to remind you that if you have many terms over one term, then you can just do this to rewrite it in that power rule format. You can just divide each term by that single term, right? If you have to actually write it out, this step you might just do in your head. But if you have to write it out so you don't make a silly mistake, this is what you're doing. I'm going to divide each of those terms by 2x cubed. Right? It's just breaking it up into a lot of little individual fractions. And you can't do it if it's the other way around. If you had multiple terms in the denominator, you can't break that denominator into separate terms. So got to have good algebra here. And now just dividing each one of those. So 8 divided by 2 is 4. X to the 7th divided by x to the 3rd is x to the 4th, right? You subtract our exponents. Minus 3 halves doesn't reduce. X to the 6th divided by x cubed is x to the 3rd. This is just a plus 1, minus 7 halves. And x divided by x cubed is x to the negative 2. And I'm leaving it right that way because now it's power rule ready to go. That's still just f, though. And now f prime of x equals 16 x to the 3rd. 3 times negative 3 halves is negative 9 halves x squared. The derivative of a constant, 0. And negative 2 times negative 7 halves is positive 7, right? 14 halves is 7. X to the, subtract 1, negative 3. And yeah, that's not good for final answer, so if you were using pencil, you could just erase that. Or you take your time and you rewrite the whole thing just to fix that one term. Doesn't hurt. Takes 30 seconds. So this becomes 7 over x to the 3rd. And at this point, I'm happy. I'm good. You could make common denominators with all these and put them all together and, you know, put it back the way it looks like in the beginning, one big fraction, but not necessary in my world. So we're good to go there. And, you know, we learned the power rule, but then just saw a lot of examples. So feel free to look back at any of these if you get stuck on the homework. And as always, if you need help, just ask. All right, good luck, kids. Go get them.